Welcome to Minukuu tutorials. In today's tutorial, I'm going to show you how to perform simple linear regression in R or RStudio for that matter. So basically, our tutorial is going to cover three major parts. The first part has to do with performing the regression, obtaining the regression coefficients, and interpreting them properly. The second part has to do with plotting the regression curve, that is obtaining our scatter plot with a regression line. And then the third part has to do with the assessment of the quality of the model. So without wasting my time, let's read our data set into R and start. I already have the data set on the desktop in the form of a CSV file. So we could name our data with capital D. Data is equal to read.csv. Let me go to the desktop and copy the file extension. So this is our CSV file here that we want to read into R. Right click on it, click on properties, and then we click on security, and then we copy the full file extension over here. Okay, then we come to R and come and paste it here in quotations. So put quotations and paste it here, Control V to paste. And we either put forward slashes or two backslashes. Preferably, let's put single forward slashes. Okay, and we are through to go. So I can actually execute this or run this to read our data set into R. So this is done. Now let's print our data set so I can show you what it contains. So print brackets data, and let's see what it contains. So we have our data set over here. It actually contains 4 variables. So in total we have what do you call it? We have a total of 237 individuals or patients for that matter, and it contains 4 variables: the gender, the age, the height, and then the weight. So if you want, we could say, for instance, if you want it this way, dimension, we use the code dimension to know how many patients are there, how many variables are there. Then we could say patient in brackets data. Like I told you, it contains 237 individuals and 4 variables. Okay, but it's nothing important. It's just to throw more light. Okay, and now it's important to note that in performing simple linear regression, you have to first of all define your dependent and independent variables. First of all, what is simple linear regression? It's a type of model, or if you want, it's a type of linear model that enables us assess the relationship between or assess whether or there is any linear relationship between any 2 numeric variables. Remember, I said 2 numeric variables. When we have more than 2 numeric variables, in that case we have to perform multiple linear regression. But when we have 2 linear when we have 2 numeric variables, or if we want 2 quantitative variables, in that case we can actually perform simple linear regression. So the aim is to assess whether there is any linear relationship between these 2 numeric variables. In our case, we could perform simple linear regression to find out whether there is any linear relationship between height and weight, for instance. That's to say, does height predict weight, for instance? So in that case, we are trying to say, does weight depend on height? So weight will be our dependent variable and height will be our independent variable. So weight, once again, is our dependent variable and height is our independent variable. Okay, now it's anytime we want to write, in R, when we want to write the name of a variable, when we want to select a particular variable, it's important to write data $, the name of the variable. So to prevent this, we can simply attach our data set, so that anytime we want to write age, we simply write age. We want to write gender, we simply write gender instead of data $gender. So to do this, simply attach the data set. Okay, and we are true to go. Now we've attached our data set, and we'll start with the first part of our tutorial, which has to do with the regression. So I would say perform regression. Part 1 has to do with performance of the regression, right? So part 1 is going to perform regression. Let me hashtag it so that I will not recognize it as a code. So we're going to perform regression. Perform simple linear regression. Okay, so to perform simple linear regression, we will use the code LM for linear model. And if you would like to know more about the code LM, you simply type $LM, okay, and then you execute. When you run it, I will give you some help on how to use the code LM. So it gives you all the arguments and their usage. You can do this, you can read it at your own free time, but for the purpose of this tutorial, I'll show you everything practically. So there's no need reading through all this. And then we will name our model. We will name our model model with capital M. So I will say, for instance, model. Our model is equal to LM for linear model, like I explained, and then into brackets we'll indicate a formula. The formula is to tell you that is actually the relationship that you want to modelize. So you are trying to say, okay, weight is a function of what? Height. In other words, weight depends on height. So you say formula is equal to weight with E. Weight depends, so the depend we use tilt, depends on height. Okay, then we put comma, and then we indicate a data set. There are other arguments, but we don't have to put it to waste our time. By default, it's okay leaving it like that. So we would say data is equal to the name of our data set. We have written it as data with capital D. So data, and we are true to go. So let me run this to perform our simple linear regression. This is perfect. And now to see the results of our model, we will use the code summary. So write summary into brackets model to see the regression results. Okay, so if I should run this, see that it has given me the results below. We have the it starts, it has recalled the formula, which is LM, into brackets we indicate the formula and then the data. But now the result starts with the residuals. The residuals is simply the difference or the variance between the the individual Y values and the predicted Y values of the model. That difference is what we call the residuals. So what R does is that it gives us it evaluates the dispersion of these residuals, by calculating the minimum, the first quantile, followed by the median or the second quartile, followed by the third quartile, and then the maximum. Okay, so this is not something that later on we will look at how to assess the quality of the model based on the residual distribution and everything. So we will look at that one later on. What's more important at the moment is the coefficients. So the coefficients here, we are talking about the intercept and then the slope or beta. So when you look at the intercept, it's telling us that the intercept is negative 132 32 point something, and the intercept doesn't really, that's the baseline. It doesn't really, unless you want to explain something, you want to explain, I don't know, it doesn't really, that's not our interest. It doesn't really tell us more about the relationship between about any linear relationship between the two numeric variables. What is more important is to look at the slope, you know, and the slope here is positive, it's 3.8. so if the slope is 3.8, then what that means is that there's always 3.8 kilograms. For instance, let's assume that the weight of the patients is measured in kilograms. There's always 3.8 kilograms increase in weight per unit increase in height. So let's say per meter height. So what that means is that when a patient weighs I mean, when a patient has a height of, when a patient has a 1 meter increase in height, this triggers, let's say, 3.8 kilograms increase in weight, you know. So since the slope is 3.8, it means that there is what is positive. So what that means is that there is a positive relationship between height and weight. However, the question is this relationship significant? That's why we have to now perform the t-test on the slope, and then to predict whether, let's say, this relationship, positive relationship, is significant. You know, so we have to look at the what we call the p-value, which is less than 0. You see that when the p-value, when you see 3 stars here, it means that it's less than 0.001, and that's to say highly significant. You know, so that's to say there's a highly positive linear relationship between height and weight. That's to say weight strongly depends on what? Height. In other words, height strongly predicts weight, because according to our regression model, the beta, or the slope, is actually 3.8, indicating that there's always 3.8 increase in weight per unit increase in what? Height. Okay, I don't have to keep repeating the explanation. But now there's another important thing to note, which is what we call the R-square. The R-square, otherwise known as the, what we call the coefficient of determination. Okay, the coefficient of determination, or R-square, is something that is so important to also note. That's what is given here as multiple R-squared, which is 0.60. 0.60 here, if we should multiply it by 100, it gives us 60%. So it's to tell us that 60% of the variation, or of the variance in weight, can be explained by the variation of what? Height. So, and you know, it has also given us the adjusted R value. Maybe we could pick the adjusted R, which is 0.5. And then this is just the standard error of the residuals. Like I told you, we don't have to waste much time on the residuals, because we will actually look at the quality of the model to access the, what do you call it, the quality. We will actually look at a plot of the residuals. We have the KQ plot and many other plots to actually evaluate the quality of the model based on the residual distribution. So for the meantime, we are done with our simple linear regression, and then we just simply proceed with the plotting of the regression curve. Okay, so let's move to part 2. And but before that, I would like to remind you of something. I would like to remind you of other things that are found in the model. You know, when I said summarize, it has only given me the key results, but your model actually contains other results. So to know these other results, you could simply use attributes. Okay, use attributes into brackets. You write the name of the model, in our case capital MODEL, and then it will show us all that the model contains. Okay, so you see that the model contains the coefficients, the residuals, and many other stuffs. You know, so if we want the residuals, we could simply write model. We use $sign to select. So for instance, if I want the coefficients, we've already looked at the coefficients over here. We said the coefficients, we have the intercept, which is minus 132 with a slope being 3.8. So if we want to have only the results of the, what do you call it, the only the coefficients as results, then we simply write model. We use the $sign to select what coefficients, for instance. So if I run this, it will give me the coefficients, you see. And if we want the residuals, we do the same thing. We simply write model. We use the $sign, sorry for that, model okay, $residuals, for instance. And if I should run this, it gives me our residuals. That's the differences between each y value for every individual, the difference between his y value and then the predicted y value of the model. So these are the residuals, and like I said, all this, we wouldn't waste much time on it. We're going to look at the distribution of the residuals later on to understand the quality of our model. So let's move ahead to the second part of our tutorial, which has to do with the plotting of the regression curve. So how do we obtain our scatter plot with the, what do you call it, with a regression line? Okay, so to obtain, so let me, without speaking much, this is the second part, which has to do with what? Scatter plot. Obtain scatter plot. So we want to obtain scatter plot and regression line. Okay, so how do we obtain a scatter plot and a regression line? There are two major methods that we can use. Okay, first of all, we can plot height and weight, and after which we use the AB line command to draw our line through. And the other way around, we can also use the scatter plot command. And the scatter plot command is contained in the package called car. So we can do it both ways. So let's start with method 1. Okay, let's start with first method 1. So in the first method, what are we going to do? We're going to use the let's go ahead. So with the first method, we're going to plot. So let's plot, let's say height and weight. Okay, so yes, say plot. Usually we plot x on y, right? So we start with the x, which is our height, comma, and then our weight, which is our y. Then we put comma, and then we're gonna indicate other stuff. For example, we can indicate the x lap, the x label to be x lap, to be equal to, let's say, our height, and then we put a y lap, y label is equal to, let's say, weight, okay. And maybe we should put other stuffs. Maybe we should put, I don't know, we should put a title for our graph. So we could, let me come down, comma, and then we could say, for instance, main for the title is equal to, let's say, regression for height on weight. Regression for height on weight. Okay, and after that, I think this is okay for now. So let's execute this, and after which we now put the AB line to plot our regression line. So if I should execute this, you see that we have our scatter plot over here. Okay, we have our scatter plot over here. Okay, very nice. So as you can see, we have our scatter plot over here of what? Weight on height, or if you want height on weight. So we have it here, weight on the vertical axis and then height on the horizontal axis. So what do we say about this scatter plot? We can see that, you know, there is a relatively linear relationship between height and weight, you know. So we can have our, you know, our line of best fit. To have our line of best fit, what do? We simply use the code AB line. So we can say, for instance, AB line, you know, into brackets, and then we say LM for linear model once again. Then we say weight, weight with capital G, weight. So we use weight depends on height, right? And then we have to indicate a data set. So we say comma data. Our data is equal to what? Data with capital D. And then we come out of the brackets. And then we could give our line any color. So let's assume we want it to be green. So we want it to be green. Then we say, for instance, our color is equal to, let's say, green. Okay. So if as soon as I execute this, it will actually draw a regression line between a regression line of best fit. Okay. So if I should execute this, see that we have our regression line of best fit over here, or line of best fit. You know, so this is the first method. The second method is quite complicated, but if you want it, I wouldn't hesitate to share with you. So this is actually our scatter plot with a regression line of best fit, as you can see, perfectly drawn. Now let me show you the second method quickly. With the second method, this was method 1. The second method for obtaining the regression line of best fit, how do we do it? So method 2, sorry, let me use the hashtag method 2. So with the method 2, what are we going to do? We're going to need a package called car. So you could say install.packages. Who knows, you probably might not have it on your car. It's CAR. Okay, I've already installed it, so I'll simply load it. So I'll say library into brackets car, to load it. Okay, so I simply select it and load it. It's telling me that to load car, I need car data first of all. So I have to load car data. So I simply say library into brackets car data. Okay, so let me load this first before I try loading. Okay, and now I can proceed with loading car. Okay, so you see that I've loaded the 2 packages. I've succeeded in loading my car right now, my car package. And right now, the command that we're going to use for this second method in order to obtain the scatter plot as well as the regression line of best fit is called scatter plot, right? So you could just write you write question mark scatter plot, scatter plot, and you have any help at all that you concerning the use of the arguments, are displayed over here, all the arguments regarding scatter plot. I'm not going to read through all this, but at your own free time you can look at it. So let's proceed with the drawing of the scatter plot. So we actually use the code is called scatter plot. So we simply say scatter plot, and then let's do that. So we say scatter plot okay, into brackets. What are we going to say next? We would say weight. We are using, as usual, we are using height to predict weight. So we say weight is a function. So we use a tilt. It's a function, or a weight depends on height, right? And then after which we're going to indicate our data as usual. So we say data is equal to what? Data with capital D. And then what do we put next? As usual, we're going to put our x labs to be equal to height. So we say x label. So our x lab is equal to what? Height. We put comma. Our y lab is equal to weight. Weight. Okay, and after which, since we don't have enough space, we can come down. So we can put comma, we hit the enter key so that we can have some space. And then we can also put main here once again if we want. So we can say regression. So we can say main is equal to regression. Sorry, here we were supposed to put into quotations. I'm sorry for that. Okay, good. Now we're going to say main is equal to what? Regression for height on weight. Okay, and what do we do next? Regression of height on weight, and I don't know what else can we change, because the regression is going to come with certain properties. It's going to come with box plot and other stuff on the what do you call it, on the different axes, indicating the median and everything for the x-axis and the median for the y-axis. So if we don't want that to happen, then we can say box plot is equal to false, right? I will show you that afterwards. So we say box plot is equal to false. And then there are other stuffs. For instance, we can put ellipse. Let me come. Okay, so let's say box plot is equal to false. And then we can also say if we don't want the regression line at the moment, then we can say reg line we can say reg line is equal to false. If we don't want the regression line, we can say reg line is equal to false, so that we can just have a scatter plot, and after which we do the rest. Later on we can say reg line is equal to true in order to have the line of best fit or the regression line. So we can say reg line is equal to false, for instance. Then we can say grade. That's if we want a grade to appear on the curve, then we can say grade is equal to true, but that is not important. And then we can also say ellipse. That's if we want ellipse on the curve, then we can say ellipse is equal to true or false, right? So but that one, let's leave that one for now. And then this, we can also say smooth, because it usually draws what do we call it, smooth is equal to false. Sorry, we don't want it to draw what do we call it, the variance function and the mean function. We don't want that, so we can say smooth is equal to false. Okay, so make sure you type in all that I've just entered. This is the first method, right? So do it as I've done. Now let's run it and see what happens. I hope you can see clearly. Okay, so now let's execute this and see what happens. So you see that when I executed it, this is what our scatter plot as usual. So this is the second method for obtaining the scatter plot. You see, now if we don't want, you see that it has given us, it has added some grades and what have you. If we don't want these grades, then we can say grade is equal to false and it will take away the grades. And now, so let's do that for instance, and you see, so we can say comma grade. If we add grade is equal to false. Okay, let me execute once again for you to see. You see that it has taken away those grades. And now if we want the regression or the line of best fit, let's assume I had said smooth is equal to true. It would have drawn certain lines. If I should just remove smooth, okay, if I should just remove smooth, or if I say smooth is equal to true over here, it will draw us the what we call the mean function and then the variance function or whatever. We don't need that. You see, if I say smooth is equal to true, you see it will draw us these lines, which we don't want. So we can say smooth is equal to false as usual. Let's leave it with false. False. But now if we want our line of best fit, right? So let me get back the scatter plot. So let me run this again. So we have our scatter plot right here. But now if we want the line of best fit, how do we get it? So then we have to say reg line is equal to a true. Over here we say reg line is equal to false, so we must say reg line is equal to true if we want the regression line. So we say reg line is equal to true, regression line is equal to true. And now we have our regression line perfectly drawn, right? You see it? So we have our regression line perfectly drawn over here. And now what else can we do? We are true to go. Now if we want to have some ellipse, so that the ellipse, the aim of the ellipse is to give us, is to just indicate the where we have the maximum concentration of the points. So with the help of the ellipse, you see how the points are distributed around the regression line, from the highest concentration to the lowest concentration. So we can just put comma here, hit enter, and say maybe ellipse. So we say ellipse is equal to a true if we want to have ellipse. Okay, and now if I should execute all this, let's see what happens. Okay, see that is beautifully drawn. See how beautiful it is. When I said ellipse is equal to true, so the purpose of this is to show us the concentration of the points around the regression line, or should I say along the regression line. You see it? So from the highest concentration to the lowest concentration. And this marks the end of what? Of the second part, which has to do with obtaining the regression line as well as what? The scatter plot with the regression line. Now the third part has to do with the quality of the model. So let's go to part 3. So part 3. In part 3, we're going to look at the quality of the model. Part 3. Part 3 has to do with assessing the quality of the model. Quality of the model. there are several graphs that we use to assess the quality of the model. The first one has to do with the plot of the residuals, or the plot of what we call it, the residuals on the fitted values. The second one has to do with the normal QQ plot. I will explain each and every one of them. There are other graphs, that comes with it, but we usually base our explanation on these two, the normal QQ plot and then the plot of the residuals on the fitted values. So how do we obtain these curves in order to assess the quality of our model? So first criteria, if you want first criteria, or you can say criterion one. So criterion one has to do with what? Plot of residuals on fitted, or let's say plot of fitted values on residuals. So to do that, all we simply have to do is to plot the model. So you simply write plot into brackets the model. We named our model, right, with capital MODEL. If you look at it over here, we named our model capital MODEL. So I'm going to plot this particular model so that I will obtain the graphs. So if I should say plot the model, it's asking me to hit return. As you can see, when I said plot model, look at what it said. It said what? Hit return. So all we simply just hit enter, right? Just hit enter, and then we have what we call the first graph is a plot of residuals on what? Fitted values. But I don't really admire this graph because it's not really looking, it hasn't given us the zero line. It's not very clear. It's looking fainted. So let's hit enter again, right? Just leave the cursor blinking in the console, then you hit enter again. Okay, when you hit enter again, it gives us the QQ norm plot, you see. But let's repeat the process once again. If I should hit enter again, there are other graphs for you see this other graph. If I hit enter again, I guess that's the end. Okay, so there are two graphs. So let's plot it once again. So let's plot the model once again and repeat the process. Just plot it. Now you put your cursor over here, hit enter, and when you hit enter, it gives us the first graph, which is the residuals versus the fitted values. So now what is the purpose of this particular model, the first model over here? It serves three purposes. The first one has to make sure that the aim of the first one is to detect non-linearity. So what do we mean by non-linearity? When the terms of, or if you want, when the points, when we talk about the points here, we are talking about individual points over here represent the people. When the points are randomly distributed, or if you want, or when they bounce randomly across or along the zero line, see that these are your residuals, right? It starts from -20 to 40, right? So what that means, and that's for the y-axis, and the x-axis is the fitted values, or that's the x-axis is the fitted values. So what that means is that when individuals fall directly on the regression line that we drew earlier on, let me show you back the regression line if you want. Let me show you the regression line. Okay, let me show you the regression line once again. We can get it back. So if you want, let's look at the regression line. Sorry for that. I want the regression line back. I want to get a regression line back so that I can explain something to you. Okay, let me remove the ellipse. I don't want the ellipse for now, so we say ellipse is equal to false. Okay, now okay, the ellipse are gone. Okay, now what that means is that, as you can see the regression line, individuals like this person over here, this person over here, and all the other people who lie directly on the line, what that means is that their residuals is 0. Why? Because there are no, when you look at the y values, somebody who lies here, when you trace over here, his y value is somewhere here, and there's no any difference between his y value and the predicted y value of the model. So the residual will be equal to 0, right? So all these individuals who lie directly on the regression line, their residuals will be what? 0. So now let's come back to the what do we call it? The residuals and fitted values curve. So let me plot back the model again, and then I'll just hit enter to obtain the residuals and fitted values plot. Okay, so now what that means is that you see that the 0 here is indicating what do I call it, the difference, or if you want, the residuals, right? That's the 0 here is indicating what should I say, the 0 residual difference is a straight line right here, and all the individuals that were found directly on a plotted curve, or what should I say, directly on the plotted or directly on the line of best fit, will be found on this particular, on the 0 line here, you know. So this is the purpose of the 0 line. And now I'm saying that when we talk of linearity, as you can see in our case, we can talk about linearity. We can say that we can talk about, and when the model is linear, then the model is linear, or the quality of the model, of the linear model, is best when the points, or when the individuals are randomly bounced across, or if you want, along this particular line, the 0 line. You see, so you see that they are randomly distributed across the 0 line. Then we can say, we can talk about linearity here. The second thing that this particular curve, that the plot of the residuals versus the fitted values, the second purpose that it serves is what? Is to detect what do we call it? Is to detect an equal error variance, or unequal residual variances. Why is this so important? When we have, let's say, the model is best when the variances of the residuals are equal. That is when they form what we call like a horizontal band along the 0 line. So what that means is that when you look at the residuals, when you see that they form a horizontal band across the 0 line, what that means is that they are residual. For instance, if assume that all the points were somewhere very close to each other, the points are very close to each other along the residual line, then what that means is that the variances of the residual values are almost what? They are very close to each other across. So what that means, since they are very close to each other, it means they are not far apart. In other words, their variances is almost constant. It's almost equal. So as we can see, you can see that our points relatively, they are very close to each other, and we can talk about talk about perfect equal variance here, but you can say it's not bad all the same, because the points are very close to each other across the 0 line. And the last thing that this particular curve serves when assessing the quality of the model is to identify outliers. For instance, when we look at this particular individual here, you see that the outliers are well identified here. We have the individual, for instance, 179, 169, and 138. You see that their values are far apart. They are very far from the rest of the individuals. You see, so these are outliers, And this is the third purpose of what this particular plot, the residuals and fitted values plot. So it also helps us identify outliers, that's individuals with extreme values, and so that in our interpretation we will not really concentrate on them. Okay, now the other curve that we can look at, or the second criterion, so this one has to do with what? Residual. The first criterion that we've looked at is residuals versus what? This is the residuals versus fitted values plot. And I told you that the second curve that we can also look at when assessing the quality of the model is what we call the QQ norm plot, or some people say QQ plot. You know, so we can say criterion. The criterion 2 has to do with the QQ or normal QQ plot. QQ here stands for plot quartile, or some will say QQ plot or whatever. It stands for quartile plot. Okay, and what's the purpose of the quartile plot? First of all, how do we obtain the quartile plot? So to obtain the quartile plot, all we have to do is to simply the plotting of the model. So you have to plot the model. So plot the model. As a matter of fact, if we should hit a return here, we obtain the plot, but I just want to repeat it. Okay, so simply plot the model. Okay, when you plot the model, the first curve that comes with it is what? Okay, you see that's the QQ plot. If I should hit enter, it gives me the norm, what do we call it, the residuals versus fitted values plot that we've already looked at. This is what we've already looked at. And then when you hit enter again, it gives you this one. It's still the same thing. Or let's plot it again. When we plot it again, okay, then we hit enter, it will give us the QQ plot. Okay, let's hit enter again. It's still the residual versus fitted values plot. We hit enter again and we have the QQ plot, or the normal QQ plot. So this is actually a plot of what? The standardized residuals. When we talk of standardized residuals here, we are talking about the residuals divided by the standard deviation. So we are talking about standardized residuals, a plot on a y-axis, and then the theoretical quartiles on the x-axis. Sometimes you see QQ plot with, let's say, theoretical quartiles on the x-axis and then sample quartiles on the y-axis. Is still the same thing. And then you have a straight line over here. And then the aim, when the model, what's the purpose of this? The purpose of this is to ensure that the residuals are randomly distributed. So for the model is said to be best when there is what? When the residuals are randomly distributed. You see, so when the residuals are randomly distributed, we say the model is best. And in that case, you see that all these points over here will lie straight on the line. But in our case, you see that there are even outliers. These outliers are over here. In addition to that, not all the points really lie on this particular line over here. But at least we could say a good number of the points, or majority of the points, lie on the line. So we could say the residuals are relatively randomly distributed, even though it's not a perfect random distribution. You know, so our model is not bad.